Hi, in this video we're going to be introducing differentiation, so we're going to find out what it is and some of the motivations of why we might want to differentiate something in the first place. Now, up until this point we've been talking about straight line equations, we've been investigating things like gradient. Gradient's a measurement of steepness, and on a straight line it's constant, so it doesn't matter which point I take on the curve, I know that the gradient will always remain the same. In this case, I've got the straight line y is 2x, so the gradient is always 2. Now, if I take a quadratic equation, like x squared, and I take a coordinate on that curve, I can see that the gradient is going to change depending on where the point is. So if I have something in this quadrant on the right, then I can see that I'm going to have a positive gradient, and as I bring it to the right it gets steeper, and as I bring it to the left it gets less steep. When I pass through the origin, I'm going to have a completely flat horizontal line, a gradient of 0. If I can get it on there, that's close enough. And then as I approach the left side, I will actually have a downward sloping tangent, so I have a negative gradient. Now, you might have done something like this at GCSE level. What we can do to estimate the gradient is we can draw a tangent line on with our ruler and get two coordinates from that tangent line and work out the change of y and the change in x from there. So for example, here's one I've already done. I've drawn a tangent line like so. I found two coordinates that are on the tangent line, so this coordinate right here is the point 1, 0.25 for x, 1 for y, and the coordinate up here is 2.75 on the x and 7 on the y. Now if I work out the gradient at this point here, I'll do the change of y divided by the change of x. So my y coordinates, or my y ordinates I should say, are 7 and 1. My x values are 2.75 and 1.25. And if I calculate that, I'm going to get 6 divided by 1.5, which will work out as 4. And I've run out of space, but I'll like sneak it over here somewhere maybe. Yeah, m is 4. There we go. So I've got an estimate for the gradient, and that might be right. It might not be. I don't know. I can do something similar over here, and this is one for you to try on your own. So use your ruler. We're looking at this point here, minus 1.5, so I guess that's like here. So I'm going to get my ruler. I'm going to put it roughly, there we go, that's not bad, is it? I'll mark a line on. Oh, that's not how you do it. Hey, that's a little bit out. Do I need to re-record this? I'm not going to. I'll be fine. We'll manage. You guys will have a better answer than me. So I'm going to take two coordinates on this tangent. I'm going to take this one here. And I'm going to take this one here. That's close enough. There we go. So my coordinates are, let's see. This is going to be minus 2.75 for the x. And the y value is going to be 5.5. And down here I've got the x value, which is minus 1. I've got the y value, which is 0.5. So I've got some coordinates, and now I'm going to chuck them into the gradient formula. So I'm going to calculate the change of y and the change of x. My y values are 5.5 and 0.5. My x values are minus 2.75 and minus 1. If I work that out, I'm going to have 5 divided by minus 2.75 plus 1. Since I've got two minuses here, that's going to become a plus. So I'm going to have 5 divided by 1.75. I don't even know what that is. Let's pause the video for a second. All right, cool. So that when I typed it in on the calculator, I got minus 3.25 out. Okay, so what are the problems with this method? Well, in both cases, I've just used the ruler to estimate a gradient. It's not accurately describing it. Some people might decide to make the ruler a little bit steeper. Some people might decide to make it a little bit shallower. And it doesn't necessarily look wrong. So we're going to get a range of answers just there. So I would say something along the lines of just there's some human error and there's going to be natural variation in the steepness. Something that we could do to at least ensure that everyone gets the same answer is we could use points on the curve rather than drawing a tangent and taking points off there. So we've done that here. We're going to take the same curve, y equals x squared. We're going to look at the gradient at x is 1, and we're going to use the points 1, 1 and 2, 4, both points that are on the curve. Now you can see already that this red line represents the gradient between those points 1, 1 and 2, 4. And when you compare it to the actual gradient at x is 1, you can see already there's a discrepancy. So it's not going to be ideal either. But we'll still work out the gradient. So we've got our two y values, which are 4 and 1. And we'll take our two x values, which are 2 and 1. And we'll get a gradient of 3. Now, if we take points that are a little bit closer together, so the point would be roughly here, I guess. And it's a little bit hard to see, but this should produce a slightly better answer if we bring those points a little bit closer together. It turns out if we work it out, that it does. But it's still not the actual gradient. So what we're going to do is we're going to rely on an algebraic method, which will cut down on the amount of time we're spending, and it'll ensure that we get the exact gradient pretty much instantaneously. So what differentiation does is it gives us effectively a gradient formula, which is known as dy dx, and we can plug any x value into that gradient formula to instantly give us the gradient. Now, differentiation is a two-step process. Whatever expression we have, what we do is we first of all multiply by whatever power we're working with. So recall the curve that we had just a moment ago was y equals x squared. So if we did that first step of the process, we'd multiply by the power. The power is 2. So we would put that in front like this. And the next step is subtracting 1 from the power. So the power used to be 2. And then I'll work out 2 minus 1, which is obviously, that's just 1. Let's just get rid of that. There we go. And then I've got my gradient formula. Now there is a redundancy here, of course, 2x to the power of 1. X to the power of 1, we don't really need to state that, so we'll just call it 2x. So here's my gradient formula. dy dx is 2x. And if I want to work out the exact gradient at a certain point, I can just plug in an x value straight in here. and then I'll know the gradient. So I'm just going to scroll down. And here's the problem here. So we've got dy dx. Again, I'll just remind you of the process. You bring the power down, put the 2 in front, and take 1 off the power. And it is technically a power of 1 here, but I'm just not going to write it. And if I wanted to work out the gradient at x is 2, I would just plug 2 into this formula. So instead of x, I've got a 2. Now I'll work out 2 times 2, which is 4. Fantastic. And I think that's the gradient I said it was. So I must have done a good tangent that time. Sorry if you can hear a crying baby in the background. It's not me. So if I do it the second time, but I plug in minus 1.5, 2 times minus 1.5 is minus 3. And I think I suspected at the time that my tangent wasn't very good. And yes, I was wrong. It wasn't miles out, but it's a different gradient. So that's the idea of differentiation in a nutshell. Hopefully it seems easier than drawing a tangent and working out points from it. It's a much quicker process than that, and we can very quickly work out the gradients if we want to.